There we go. All right. So the first thing we'll do is to finish up this program, okay? Because I think you guys might want to know how to do this code and how to test it. If you turn in something that is that compiles, that assembles, but it doesn't quite get a job done, I will actually go read the code and give partial credit, okay? But it has to at least assemble first, because people just kind of copy and paste it from some AI. Yes, they just paste it into AI and they get like give me the code of this, and then the AI would use the instruction set of some other architecture. Even if you upload the opcode table and all the notes in this class, it is really difficult to convince AI to only use the instruction set for this class because I have tried. If I have tried and could not quite get it done, it means it's really, really hard to get it done. So that's why I see instructions that do not even exist in this architecture. It's like, where did you get that? Well, I know exactly where, but yeah. All right. So let's go ahead and get this started. All righty. So we got all the initialization. We just have to implement the function f. So what I'll do is I'm going to go to the C code and just kind of copy and paste, the line of the 3 lines from the C code, and then we'll start with that. Okay, so we'll comment out every single one, all the lines, so that we can just go ahead and get started with this. All right, so typical thing that I do, I always do the return first before I forget. So LDBD, um, increment D, and then JMPB. Okay, so that's always the return code. And then I go back here and I ask, do we have any local variables? Nope, we don't. And then we specify where do we find our parameters. So PTR is FLVS 1 plus. That one has to do with the return address that is pushed on the stack. And then the other one, which is VPTR, is f underscore ptr 1 plus, because the parameters are pushed backwards, which means the last parameter has the highest possible location, and then in other words, the first parameter has the lowest location. So that's why we specify the order like this. Okay. And then what we'll do is we're going to put a halt instruction here just to see what the stack looks like by the time we get here, just so that we know that, oh, okay, what is PTR and what is VPTR. And then this is main, okay, which is corresponding to the actual main in the C code. So if I go to struct.c or struct2.c, this is what main looks like. Y should get a value of 0, and then we call f with n1 as the address, or the address of the first element of n1, and then we also pass the address of y. So y is a unsigned 8-bit integer, so but we should know where that is. Okay, so we'll switch back. Okay, and then we take a look at how the offsets are defined, because this will give us a clue as to where I can find x and y as local variables of main, and also how we're supposed to push the parameters and what we should be seeing on the stack. So that would be the first thing that I do, and we just do the usual things. We go back to the oh, okay, I jumped one too many levels. Okay, getting back to shared. Create a folder, create a new sheet for today's lecture. Do you guys go back to the sheets and, download one, maybe annotate it, add some colors and whatnot? You do? Okay. Yeah, so it can be helpful, okay, because it's a somewhat of a visualization of what is on the stack. And I do it very consistently in the same way, right? 255 is the highest location, and then we just, kind of look at this one, -1, and then we have decimal to hexadecimal, like so. And so with this one, I actually need quite a few locations. So I'm counting right now in my head. This is the return address, and then we have Y, and then we have X. So now we have the entire frame for main. And then because it's a recursive call, every time you do a recursion, it's going to take up 3 bytes. So it should have 6 levels of recursive call. Okay. So that means if I really want to show, how the stack is going to be used, it would go all the way to like this is 1, 2, 3, 4, 5. Oh, okay, I lost count. Okay, we'll go back and do the actual arithmetic. Okay, so 253 minus 18 would be where the stack pointer should not touch anymore. So that would be what, 245 minus 16. So that would be a 7, 237, I think. Yeah, 18. Sorry. So I was wrong. Okay, it's 18. So that would be 235. You're correct. So 235, which means we need 2 more locations. So that means the stack pointer may go as low as this, okay, or it should. So now we go back and annotate, what each location is used for. This is the usual thing, which is the return address from main to the entry code. This would be y of main. This would be x of main. And then we have the parameters that we push on the stack from main when we call the function the first time. So this would be vptr of the function, and then this would be ptr of the function. Um, so because vptr is the address of y, so we expect that to be an fe, and then PTR is the address of the first element of the array. So I cannot tell right away because I need to kind of run the assembler to figure that out. But we can just kind of say, okay, we can just say this is going to be the address of n1 bracket 0, okay, because it's the first element. So we'll just kind of put in some comments like this. This one, depending on the entry code, this is using LDD0. So that means this one should be a 09 to get to the halt instruction. And these two are unknown because we haven't, oh wait, we should actually know one of them. We should know one of them because it is initialized. Um, so if we go back to the C code, we can see that, Y is initialized to a 0. So that means, this location should be a 00 here. We should see a write operation to RAM to that location of a value of 00. So that's what I should be seeing just based on the program at this point. All right. Do we have any questions about what I just did? I'm trying to figure out the layout of all the memory locations by the time we get to the entry point of F here. So this halt instruction will stop execution, and I really wanted to stop just so that I can confirm what the stack looks like and does it match my expectation. So that would be kind of the first thing that we do. All right, so save the code, and then we'll run it in Reefer Spider. Okay, so document CISP 310, Reefer Spider, submit struct2.ttp.asm. There we go. All right, so it's all done. We go back to the assembler, and then we try to confirm those locations. FF is getting 09, very good. FE is getting 00, that's good. That's variable Y getting initialized to 0. Location FC is getting FE. I think that was also matching our expectation. Yep, okay. And then the last thing is where is N1? And we can find that out in the assemble view because N1 is a global variable. It is what we call statically allocated, which means the assembler itself is responsible to allocate that space. It is not allocated at runtime on the stack. So we are looking at this. It is supposed to start at location 0A. And now we can go back to our trace and see if that is the case. We go to the assembler, we go to the analysis tab, and we should see FB being initialized to F0A. And then we have the return address push. I forgot about that one. So I should probably just kind of add it back because I forgot. So this is going to be the return address from the function to main. And all right, so do we have any questions at this point? So everything is as expected right now. Okay, so now I can go back to the C code and try to find out what I'm supposed to do with this. I think the first thing that I need to point out is plus equal to is a compound assignment operator. It essentially returns the value that eventually got stored over here. That becomes the actual value of the compound add operator. Okay. Um, so what we can do is simply to say, okay, what if I change the C code to something that's simple, it doesn't really do much, and all we want to do is to replace this entire right-hand side of the compound add with something that is just a constant, okay? Because I want to make sure that I understand how to do this without all the complexity. So I'm just going to change this to, I don't know, 43. Okay, and I want to implement this code, make sure that works first, okay, and then I'll go ahead and replace the 43 with that, kind of increasingly complicated thing. All right, so how do we do this? Okay, so let me just kind of paste it over here to kind of remind ourselves what we are trying to do. So the right hand side of this is pretty easy. I'm not too concerned about it. So my main concern is about the left hand side. So the left-hand side, I need to get to VPTR first, okay? So that means, I need to get to first, we need to get to the offset. Yeah, we need to get to the offset. I was thinking, which register to use, okay? That's why I rolled my eye. So FVPTR, that is the offset to the parameter. And because it is the offset from the base of the frame, and at this point, the stack pointer does point to the base of the frame. So now we can say add BD in order to get to the address of VPTR. And then we do LDBB. So now B is PTR itself. Are we good? Okay. So now I have to think a little bit more carefully. Okay. So I'm going to do another LD, in this case, A, B. So register A is now the current value of what PTR is pointing to. Okay. So let's just say that you're doing this, and at this point you're gonna you're losing track of what register has what. Okay, and you need a confirmation. So we can stop right here. Okay, so we can just say halt, and then we put in some comments here and say that A should equal to whatever VPTR is pointing to. And based on the way we pass VPTR, so that should be the address of local variable y of main. So this really should be the address of y of main. Are we doing okay so far? Okay. So right now I'm only using or mostly using understanding of the C program to predict what the assembly code should be doing. Okay. So since yeah. Oh, actually, I misspoke. VPTR is the address of y, so we are now looking at the actual value of y. So register A should have the value of y. So I misspoke. Mhm. All right. So, but we also know that by this time, register B is VPTR itself, and VPTR itself is the address of Y of main. So I have two things to confirm. Okay, because the value of Y is not easy to see because it is just 0, but I should be able to verify that register B is a pointer to that location. Okay, so that's what I should be double checking and verifying. All right, so we run the code, and this is also why Rufus Spider is kind of important, and I can help you kind of figure out what to do with yours. Did you Can you see the drive in Windows on this machine? Okay, we'll take a look later. Okay. So we now go back here, and we can see that register. Okay, did I? Nope, this is not updated. I forgot to save first. Control G. Yep, I forgot to save. Go do it again. All right. So now we should see that register B is FE, and then register A should be 00. Okay, that's what we should be seeing, and we'll go check it out. Okay, register B eventually become FE, very good, and then register A becomes 00. So I just verified my understanding of this code. So that's actually important, okay, because you write any additional code, you kind of have to know, okay, what is this doing, what is this doing, and so on. All right, so now we can continue because now I have double checked the code. It is working the way it's supposed to at this point. So what I need to do is to say, okay, what about the rest? Okay, so now take out the halt instruction. I'm going to load register C with the 43 and LDI. There we go. And then we add the C, register C to register A. That's what we need to do. So we add AC. And then after the add, we store back to whatever register B is pointing to. That would be A over here. And that's it. Okay. So I just have to say that this is going to update local variable y of main to 43. Because y of main was a 0, if I add 43 to it, it should be 43. Is that okay? So the key to get this part to work, or in the exam, in the final exam, to spot any problem, is you have to track what each register has. Okay, and you have to relate it to the C++ concept. So you have to relate it back to, am I seeing the offset to a particular thing on the stack? Am I seeing the address of something? Or am I seeing the actual value of that something? So you have to track all of those things, and I would not use my mind to track all of those. Okay, I would actually just write it down. Okay, all right. So I'm going to pause here again. Okay, so I'm going to pause. Okay, so put another halt instruction here. Um, and the register A should also be 43. So Y of main should be updated to 43. Then register A should also be 43. So now we go back to Reaper Spider. Just run it. Because this way I'm double checking the code, really step by step. I'm double checking all the mechanisms and see whether they work or not. All right. So are we seeing location FE to update to 43? So what is 43 in hexadecimal? 43 in hexadecimal is 32 plus 11, right? The 32 is 2 times 16, so that means we have a 2, and then the 11 is B in hexadecimal, so 2B is the correct representation or hexadecimal representation of what we know as 43. So everything is checking out okay. Are we still doing okay so far? Okay. So now I can go back to the code and go like, okay, so we can do the plus equal, okay? We can update whatever VPTR is pointing to. The only thing that is kind of missing here is I'm not supposed to do the 43, okay? So we take out the 43, and now we go back here, and then we say, okay, we need, our current task is now to say load um, something into register B as the right-hand side of the plus equal to. Are we doing okay so far? Are you guys understanding which part of the code I'm trying to tackle at this point? Okay. So now I can take this out because I just tested this to be working. So I look at this mess here and go like, ugh, that is still a big mess. I don't want to deal with a mess that big. So now I take out the recursion. Okay, I just take out the recursion and go like, maybe just try something a little bit easier. 23. Okay, so what I'm doing is I'm simplifying something that looks really complicated into just one step easier. Okay, so that it doesn't have recursion. It's not going to go for the infinite recursion thing, or very unlikely that it will go into an infinite loop. But I just want to check whether I can test whether pointer is null or not. Depending on whether pointer is null or not, I'm going to either add 23 to whatever local variable y of main has, or I'm just going to leave it alone by adding 0 to it. Okay, so this is what I'm trying to determine. And because adding 0 is not really visible, I'm just going to go like, okay, make it something that's non-zero. So this way I can test the code to make sure that it can make that branch correctly. Because if it is a 0 and it doesn't execute, I cannot tell whether it just did not execute because it also defaults to 0, or it executed, but I'm just adding 0 to something, adding 0 to 0, which ends up with a 0. So this way I can be sure. Okay, so we'll go ahead and, because this code here, okay, whatever is following here, this code is already handling vptr plus equal to whatever register C has. So my only job is to load something into register C correctly. All right, but I can still reuse all the registers, okay, except for register C, which has to store whatever this expression ends up to be. So that's the interface between the earlier code and the code that I have written so far. Am I, are we still understanding the approach? How to break a bigger problem into smaller problems. And then the smaller problems need to have a clean interface between them. So right now, the clean interface is register C. Okay, the top part of the code has to figure out what goes into register C, which is representing the right-hand side of the plus equal to, but then the other code can handle the rest. Okay, we verified that it can handle the rest already. So we now have to deal with this part here, which is a ternary expression. And the first thing we need to do is to figure out whether PTR is null or not. Okay, so now we just have to do pretty much the same thing. Get to the offset, f underscore PTR, get to the address, um, and then we get to the value. Okay, so we do LDBB is fine. Okay, we can overwrite register B because nobody cares about the address of PTR after this point. LDI B, oh no, it is LD. It's LDB with parentheses B. Okay, I really like my syntax highlighter. I actually have to learn how to specify the syntax for syntax highlighting in Vim. It's not too hard, but it's a few extra things to learn, which is kind of cool. All right, so B now has PTR. I just need to know whether it's null or not, so I can still use the old trick of AND BB. If it is 0, then we go to the else case. So the else case is just going to be represented like this. This is going to be the then case. And then the then case has to go over the else case. So JMPI to F underscore and if 0. And then the else case label is going to be here. And then this is going to be the else case code. And then this is where going to be the end if of the ternary expression. So you can probably see from multiple examples that this is the way I code. I look at the structure first, okay, and then I backfill, what is supposed to be between the main branches, okay, because this way I don't easily forget about the structure itself. I have the whole structure already in place. I just have to now backfill. Oh, by the way, what am I supposed to do if the condition is true? Well, backfill over here. What am I supposed to do for the else case? Backfill over here. To my mind, that is easier. Now, whether your mind works the same way or not, I cannot tell. Okay, I can only tell you that this works for me. All right, so what do we do in the then case? That's easy. LDIC with 23, and then over here we have to do LDIC with 11. There we go. All right, so I think we are ready to test this code. Okay, so the way we test this code is to say that we should end up with the else case, we should end up with the then case for this at this point, because I'm passing a non-zero PTR to the function. Okay, so we say that we should This should be the result. Okay, this should be the result. And then we say that this should not be the result. So I do this because the trace would actually show the comments too. So that means one quick glance at the output in the trace, and I can tell whether it's doing the right thing or not. Okay. All right. So make sure I save this code before I run it. Okay. I keep using uppercase W because here we go, and then submit. So it's not just the solution of the assignment that is important here, it is the approach. Okay, how do you break something that is really complicated into smaller steps? And then you incrementally test the code so that each step you verify first before you move on to the next one. All right, so we go back to the assembler, and all I really need to confirm is whether this should be the result. Yep, we see that. So we are good, okay? Because the rest of the code should, so this time it should store 23, which is 19, no, 17. So that's 17 to location FE. So we double check. Yep, it did store 17 to the location FE. So this part is working. But I also need to test whether the else case is working or not. So that means I need to go back to the source code, just kind of hack the program to test it. So I need to make sure that I make a note of that. Okay, comment out this code, and then over here, and we just say, to do remove after test to remind myself. Okay, get rid of this, change it to a 0, so it's a null pointer, and save the code. Oops, save the code, and then run it again. So it would seem like it is very tedious, okay, but it is this way you don't have to look at 25 lines of code and try to figure out why it's not working. If this is not working, I can look at like 6 lines of code or 5 lines of code and try to say, okay, out of these 5 lines, why is it not working? So now we go back to the trace, and it should say, the wrong thing. Okay, 0B is correct, but it would say the wrong thing, right? It should not be the result because I forgot to update the comment. Okay, all right. So it is working. So now I can go back, change everything back to what it's supposed to be, okay, like that, and then go back to here. And now I now have sections of code to specify to the original code. So the original code is rather easy. The else case is just a 0. So that means the 11 should be a 0, which means this 11 here just should be a 0. Okay, that's an easy one. So now we can really go for the recursive case. Okay, so the recursive case is, so I have no other choice but to fully implement the recursive call because that's the only thing in the then portion of the ternary expression. I cannot simplify this any further. Okay, so now we'll go here, okay, and try to implement the then case. Okay, so I'm going to update this, okay, because we are not doing that anymore. We are now doing that. All right. So I can also, okay, if I want to really have focus, I can now, just kind of customize this and say, what I really need is for this expression. I think we have one too many. No, this is the correct one. So we want register C to equal to that. That's what we want to do. So this is a reminder for myself and go like, okay, what am I supposed to do here? I want to evaluate, oh, wait, okay. I misspoke here because we got a condition part already handled. So all we are left to do is to do the recursive function call. Whatever the value is supposed to be, we store it in register C. That's what we're going to do here. Are we still doing okay so far in terms of how I broke the problem into smaller parts? And now I have no choice but to implement the last portion of the original problem. The interface is register C. That's the important part. All right, so we're going to take out this, and we're going to take out this comment here, and then we'll go ahead and implement the recursive function call. So when you look at the recursive function call, so typically there are a few ways to push your arguments. you can calculate as you push, or you can pre-calculate everything and then just push the register. But if you use the latter approach, just keep in mind that we only have 3 registers. Okay, so my usual approach is to calculate as we push. So that's what we're going to do this time. The first thing we need to push is the last parameter. So now the first thing you need to do is to spell it out correctly, articulate what that argument is about. It is the address of member V of the structure that is pointed to by PTR. Okay, so that's how I would spell it out. If you write it out, then you can figure out the dependency, which means everything starts with PTR. Okay, so that means we have to get to PTR and then we'll figure out the rest. So we do LDI, and whatever register you want to use at this point does not matter. If you use the wrong register at the end, we can just do a CPR and put it back into register C. So we don't really have any restrictions. So I'm gonna pick register A, and I go like, okay, this is the offset, this is the address, and we need the value of PTR. Okay, so this is the value of PTR itself, which is the address of the structure. I need another register to store the offset from the start of the structure to member V of that structure. So this is what that is going to be. I think it's node V. Okay, I'm going to double check, make sure that is the correct name. Yep. All right. And then we have to add those two. So we have to do a add. Now, whether you add AB or BA really doesn't matter. I'm just going to put it as add AB. So at this point, I should have register A should be the address of the whole thing already. This should be correct. Okay. So before I push it on the stack, I want to double check. Okay, because that's a lot of code already. So by the time I get to halt, this is what I need to double check. Now PTR is pointing to the first element of the array. So that means register A should have the address of member V of the first element of the array. So now we look at how the array is initialized. I think it's before. There we go. And so we should be looking at a 5 here, or the address of this 5, which is essentially just N1. So that's what we should be seeing. And I'm going to comment and say that that is what we're supposed to see. Okay. So we say this is supposed to be register A should be the same as the address of node or N1. There we go. All right. So now we save the code and just run it. So a lot of what you need to do for this kind of coding is really understanding the C code first. Okay, not understanding what the structure is or what pointers are is there's just no way to get past that hurdle. I mean, you really need to understand all of that. So now we go back to here and then we ask, did we just put the address of N1 into register A? So we go back to the assemble tab. Okay, we look up, N1, and N1 is indeed starting at location 0A. So we're good. Okay, so know that that is good. Now, we can, if I were using GitHub, I would be checking in or committing the code to the repository. So this way, if I did mess up the program later on, I have a backup and say that, okay, this code works up to this point. I know for sure. Okay, so that would be kind of helpful. All right. So that's something that we can just push right away. Decrement D, stda. So that would push the address of member V of the structure the pointer is pointing to. So now we can move on to the first parameter, which is the value because it's not address of. So this is the value of member N of the structure that PTR is pointing to. So looking at this code, I go like, I could have done a little bit better here. Okay, so the way I look at this is I have to recalculate, PTR. So if I just move things around a little bit, okay, instead of adding AB, I can do a add BA, and then change this A to a B, and then change this A also to a B. So the reason why I want to do this is not to destroy the value of A, because register A already has the value of PTR, which I also need down here. Okay, so this saves me the trouble of having to redo the code to figure out PTR. Okay, so now I can, after the push, I can now specify the other parameter. So now we just have to say, oh, okay, that would be pretty easy because I just have to add load A with, um, oh, sorry, B, because I'm keeping A. So we have to load B with the offset to the N member or member N. Once again, add BA. So that would be the address of member N of the structure the PTR is pointing to, but I want the value. So that means I have to dereference it once. So LDBB. So now register B should be PTR points to N, or I should say member N of the structure the PTR is pointing to. Okay, and what is that supposed to be? Okay, so that's the first N. So if I look at the initialization of the code, that would be just the next location. If this is 0A, this is 0B, and the value stored here is 0C. Okay, so 0C is what I should be seeing. So when I put a halt instruction here, I'm also going to comment and say register B should be 0C. Okay, are we still doing okay so far? All right. So if you are a little bit rusty on the C++ concepts like pointers and structures and stuff like that, well, the good thing is I'm double checking. We are recording. That would suck if I did not. So we are still recording. So you can review. Okay, if you're a little bit rusty with C++, what a pointer is, how do we use address of and that kind of stuff, review that material first. Okay, and then you can always come back and rewatch the video at any point in time. All right, so now we make sure I save the code. Save, there we go. And then we just run it again. So I'm really double checking everything step by step. Okay, I'm not, you know, writing probably 6 lines of code without checking. All right, so now we go back to the analysis tab, and then we go to the halt instruction. Aha, very good. Okay, register B is supposed to be 0C. Register B is getting 0C in it. Okay, so is this a 100% foolproof method to make sure the code is working up to this point? The answer is no, okay? You can still end up with 2 bugs that cancel out each other, okay? There are such situations that you can have 2 bugs and for some strange reason, they quote unquote cancel out. So it would look like the code is working, but it's actually not. The chances of that happening with this kind of program is really slim. So that means if you see something like I'm confirming, everything is working and it is, as confirmed, then you're probably okay. Okay. All right. So now that we have checked it up to this point, the rest is pretty easy. Okay, because we just have to push this on the stack. So we have decrement D, std b, and that pushes both parameters on the stack. And we just have to do another LDI. This is the return address, okay? Because I don't need register A anymore. We are done with the use of register A. Decrement D, stda. So that pushes the return address on the stack. I have to call the function, which is really just a JMPI at this point. We got everything pushed on the stack already. When it does return, it is going to have to increment D twice because I have 2 arguments or 2 bytes of arguments on the stack. And those 2 bytes should be gone because the function call is also done. And that would put the return value in register A, but we need it to be in register C for the rest of the code to work. So I have to do a CPRCA to interface with the code that is later on. Are we good so far? All right. So I think I'm done with the implementation of F, but the way main is set up right now, using element 0 of n1 or the address of to test the whole thing, it's going to have a whole lot of levels of recursion, which is not going to be productive. So I'm going to change the code a little bit, okay, just for testing purposes. So I'm going to go to main and go like, okay, this is not what I want to do at this point. I just want to test it with maybe just a 0 first, just a null pointer. Because if the non-recursive case is working, then at least I know I won't get into an infinite recursion, right? Or at least in theory it should not. So that's why I'm testing it with a 0. So basically we are saying we're calling f with a null pointer, and then the other one is still meaningful, which is the address of y. So this is what it is testing, which basically means we are not doing anything to y because we end up adding a 0 to y and returning a value of 0 to main, which it would use to overwrite x. So that means location fe should be overwritten by 0 again. Location fd should also be overwritten by 0 in this case. So we'll go ahead and check whether that is the case or not. So we saved it already. We just run it. All right. So we get back here, and unfortunately, I forgot to get rid of the halt instruction. Uh, yeah. Where is that halt instruction? It is on line 56, 76. So 76. Yeah, I forgot about that one. So take that out because we are pretty sure it's working. So now we run it again. And double check. Here we go. So this time I can focus on just the overriding of the locations. This is the override of location FE, confirmed. The override of location FD, confirmed. The program stops at the only halt instruction on line 7, confirmed. And the stack pointer returns back to location 00, confirmed. Okay, so the non-recursive case of F is okay now. Okay, I'm pretty sure that's working. So if that is working, the next thing to test is not to go for the full test case, but to go for the next most complicated case. So the next most complicated case, if I were to show you the C code, um, struct2.c. So the second most complicated case is to change n1 or the address of n1 bracket 0 to just 1, to the last one, which is 4. So if you are to make this change to the actual C code, you can observe what it is going to do to Y and X, and then we just have to make sure that the assembly code is doing the same thing. Okay, so that's exactly what I'll be doing. Okay, I save this code, and then I go back to my temp folder just to retest it with the modified code. So I go gcc-g-o struct2 struct2.c gdb struct2, list the program, and I'm just going to put a breakpoint on line 24, okay, and just let it run. And when it's done, I look at what is x, it is supposed to be 9. I look at y, it is also supposed to be 9. Okay, so I'd have to double check. I would do the same modification to my assembly code. I should still end up looking at FE, that should be 09. I should be able to look at FD, location FD, that should also be 09. Because even though the C code over here has, the addresses are much longer and there are many differences, the logic has not changed. Okay, so that means the logic of the assembly code should do exactly the same thing. All right, so get rid of that. Pop D. and then go back to my original code over here. Go back to here. So, so my next challenge is to say, okay, but how do we change this to um, what we need, which is the address of element 4 of n1. This is what we want to do. The question is, what expression do I put here? So I'm gonna do it really quickly, and then I'll explain. So n1 is already the label of the beginning of the entire array. So what I need to do is to calculate the offset from the beginning of the array to the beginning of element 4. So that means that 4 is going to be useful, right? I also need to know the size of a node because this is an array of nodes, of struct nodes. So node size is going to be here. We do the multiplication, and then we add the product of the multiplication to n1, and that should end up as the address of element 4 of n1. Have I gone through a step-by-step approach to look at how to evaluate RPN, reverse Polish notation, in this class? I did? Okay. All right. So that's, we can double check, right? We can always double check on line 97. Are we pushing the right address on the stack? Okay, so we'll remember 97 as the line number. Make sure we save the source code and then go back and run it again. All right. So now we are back to here. First thing first, we want to double check what is the address of element 4 of n1. This is element 0, element 1, element 2, element 3. This is element 4. It is supposed to start at location 1, 2. So 1, 2 should be pushed, okay, or should be loaded into register A on line 97 when the code runs. So now I switch back to the analysis tab and I look for that line, which is line what, 97, I think. Yep. And register A out of this LDI instruction did get a value of 12, or 1, 2 in hexadecimal. So this is the kind of stuff that I check. Okay, I think this code should do this. I run it. I double check it first before I check anything else. So now, once I know I'm pushing the right argument on the stack, then I can go all the way to the end. If I feel kind of, ooh, this is not good. Hmm. Location 1, 2 is updated to 0, 9. That doesn't look good at all because, um, okay, so this is, the store is good. Okay, we're supposed to store a 0, 9, but only to variable y of main, and that is not the location. Okay, 1, 2 is not the right location. Now, 1, 2 is important. We know 1, 2 is important, but it's not the right place. So now the question is, how did we get to the wrong place? I'm so glad the program is not working. Woohoo! Yes, celebration. Okay. All right. So if it's not storing to the right location, that means register B is wrong by the time we get here. So if register B is wrong by the time we get here, that means it is wrong in this, at this point. Okay, we can see that it is loading from F9 to so location F9 has a value of 1, 2. So that part is wrong. And then we go back a little bit more. Okay. And B is 0, 2. So that is VPTR. So that means I changed the wrong instruction. I changed the pushing of VPTR to 1, 2 instead of the first parameter. I changed the wrong parameter. Okay, so that's my suspicion. I made a poo-poo because I changed the wrong instruction. So now I go like, okay, am I supposed to? No, this is not the wrong thing. Okay, so it is pushing this next. And all right. Well, then we have to go even further before this. Okay. Um, so something overrode the location. Okay. There's a 1 2 overriding some location. All right. So we have this overriding the location, and that's us pushing. That is not pushing. Is that pushing? Yep, that's pushing. And this is the recursive case already. Okay. All right. So that means the error happened even earlier than that. All right. So we have to look at how 1 2 is pushed on the stack. And I did something. There we go. I just typed Control Z because I typed something where I'm not supposed to, and that's what's causing column G to disappear. So Control Z, basically undo what I just did. All right. And okay, so we are looking at what we are pushing on the stack. Pushing FE on the stack is good, okay, because that's just pushing the 1 2 is supposed to be correct too, because that's pushing the address of element 4 on the stack. This is the return address, which is all good. And now we are in function F. In function F, we look at PTR, and then we look at register B. Okay, PTR is non-null. It is 1 2. So far so good. Okay, everything up to this point is correct. And then did not go to we did go to the else case. Wait, JZI. We did not go to the else case because this line 40 is in the then case because of the comment. It's spaced out a little bit, and then we retrieve PTR, and PTR is indeed 1 2, so that's still good. And then we look at the value V over here. So we're pushing V member V on the stack, or the address of member V on the stack. That is still correct, okay? Because member V is the first one, so we push 1 2 on the stack. That is actually correct. And then we push member N on the stack. And member N should be a 0. It should be a null. Okay. So that's offset 1 from the beginning of the structure. So this is location 1 3, which is where we're supposed to find the 0. You found the 0, so everything is still good. Decrement, and then we push that on the stack. I know what. I reversed the order. Let me see. Did I reverse the order? No, I did not. Okay. Oh, okay. It is supposed to do this. It is supposed to do this. In other words, there's nothing wrong. It is supposed to do that. Tac, you have to go back to retake CISP 360. Okay. So if you look at the C code, so I'm gonna crash Kakashine's class and go like, I'm going to self demote to have to retake CISP 360 because I did not read my own code correctly. All right. So when we look at the C code, okay, so if you look at the C code, that's okay. We can put it in read only mode. So when you look at the C code, um, because we pass the address of member V to the recursive call, and that gets overwritten over here. So we are supposed to see that. Okay. So the trace, there's nothing wrong with the trace, okay? It is doing what it is supposed to. Location F9 is supposed to be overwritten, and so that is okay, okay? So this is fine, okay? Not a problem. And then we go further down, we can see this is Y getting overwritten to 09 in main, and then this is X getting overwritten by 09 in main, so everything works out. Okay, so I was, so it wasn't a bug. Well, okay, it was a bug in my understanding of the C code, but it wasn't a bug because I actually implemented correctly. So that's a kind of rare um how do you call it, dissonance, because I actually implemented the mechanism correctly, but I forgot that it's supposed to change that location. All right, so the code is working. We can now release. We can change the code back to N1, the element 0 of the N1. So now we can just kind of run the code as it is intended. Okay, so we just pop this back here and then go back here, change the code back to what it was before, like so, and just let it rip. Saved again. Okay, there we go. Oop, there we go. While it is doing this, I'm going to go back to the C code and make the corresponding change, just so that the C code is now also consistent with the assembly code. So you can do it like this, which is the same as what we had before. Okay, by the way. So this is the same as the original code. And we go back to the trace. We go all the way to the end. It is a little bit longer now. And we can see that we balance the stack, gets to the halt instruction, and then we store a 1F, which is 331 to, this is X of main, and Y also has 31 in it. So now we can go back to the command line interface and then run the C code and see if that is the same thing. I believe it is, um, but we'll double check. So we look at struct.c. Okay, that is already saved. So we do a GCC, GDB, list the program, put a breakpoint on line 24, run it. What is in X? 31. What is in Y? 31 also. All right, so the whole thing is working. Now, if you want to see how the structures inside the array got changed, you can also print N1, and that will show you, how the values of V have been changed. So this is not what it used to be. Basically, this becomes the sum of itself and the 9. This becomes the sum of that and also this. And then this becomes the sum of whatever it had and the 23. And this becomes the sum of whatever it had and the 26. All right. Do we have any questions other than how are you cooking that turkey? Nobody cares. Well, okay. So if you did not get the program to work, don't worry about it, right? Because the point value is okay. So you know where you made that poo poo, right? Okay, that's good. Okay. Mm-hmm. Mm. Mm. Oh, it won't compile? Okay. Okay. So the whole process of doing this is studying. Even if you don't get it working in the end, it is still studying because the whole process of trying to figure out, okay, I'm seeing this expression. How am I supposed to implement it in assembly? That whole mental exercise is the point. Okay. Now, getting it to work obviously is even better. Okay. But if you cannot get it working, it is still not a loss. Okay. Because that is time spent actually studying. This class has the same number of units as CISP 300, which means whatever number I had on here before, which is 5 hours per week. That is kind of a reasonable assumption that it will take you at least that long to implement these programs. Some people will take longer, and some people will take less time. But uh, budgeting at least 5 hours, for the homework is reasonable because the homework is your studying. Unlike your calculus class, okay, the homework is just busy work, okay, and you're trying to understand the concept mostly from the lecture or from the book. For this class, the homework is the studying part because the actual agreement between the caller and the callee and the concept of a structure, an array, and pointers, those are actually easy concepts. Okay, putting it in use to implement the assembly code, that's the hard part. Okay, so do we have any questions about the assignment that was due earlier today? Did I give you guys the exam from last semester? So it's a good time, okay? I know you guys have, lots of ideas of how to spend your Thanksgiving weekend. But spend some time, okay? Now is a good time to start to think about your strategy for the final exam. The format would be the same. The code would be different, okay? So you kind of have to go through that whole thing, go through the final exam from last semester. Go through that, use whatever amount of time that you want to spend on it or can afford to spend on it, and then think about the process. Okay, what would be the best strategy to answer those questions? How do you spot a problem? What do you think you want to bring with you to the exam to help you with that process? So that's the kind of thing that you have to start to think about. It's the strategy of how to tackle the final exam. Okay, what notes do you want to bring with you? What type of, maybe you need a ruler to line things up. So maybe you need to bring that. If you like to, identify the beginning of a construct and the end of a construct with a color pencil, bring your color pencil. Okay, so you can do this, right? You can say, okay, this is the beginning, this is the end. Am I matching the beginning with the end? Okay, so there are lots of little things that you can do. But until you go through the final exam from last semester at least once or twice, you won't be able to come up with the strategy that works for you. Just because something works for me doesn't mean it's going to work for you. Okay. And then the other thing is you can also practice by trying to annotate what is in a register after each line of that program, because that is actually what you need to do in order to answer those questions. Okay. Um, sure. Let me Let me do two things. One is to show you what assignment that you have for next week. I'm giving you until next Wednesday. December 3rd is next Wednesday. So that's for your next homework assignment. It is also a recursive program using struct. Okay, so that's part of studying. Okay, it actually coincides with trying to answer the final exam question. But before I forget, I'm going to send you the key to the final exam. So add to announcement, key to final exam, key to the final exam from spring 2025. Let's see, attached. All right, so let me see if I can remember the path to that thing. 310 1253 fxk-000 dot pdf. Wow, I can actually remember the whole thing. That's the power of being systematic. Okay, everything is systematic. Okay, if you turn everything into a system, things will work. Very in a very predictable and reliable way. There we go. So now you have the key. All right. Any other questions? Yep. hmm So a destination. Okay, so let me take a look. Which line is that? 141. Okay. So it means you have to tell me what. In that case, in order to get the points, you have to tell me what is in the register that got updated after an instruction. Yep. So there's a range. So there's a begin and there's an end. Yep. Yep. And then the key would actually answer that question too. I think the key actually has those lines already documented. Yeah, so the explanation part here, it tells you exactly what should be, how the answer is supposed to look like. Yeah, you can forget about the block thing. The block thing is really kind of more of a debugging thing for myself. But this should give you the answer to all the spots where there are problems. Yep. All right. Any other questions? No other questions? Okay, one more thing, one more tip. Okay, so as you work on the programming assignment, for next week, for next Wednesday, as you work on it, think about if I need to do something like this in the final exam, what is going to be helpful to bring with me in the final exam. Okay, because that's what you can do. You still have, oh, one more thing. When is our final exam, right? So our final exam follows the final exam schedule of ARC. So the quickest way to find it, I find, is to look up ARC final exam schedule instead of just using our own website to search for that. That takes forever. So we look at daytime classes. This is a Monday, Wednesday class. We start the class at 10:30. So that means, this is the time slot. I hate Bucky, man. Every single time we get to this page, here's Bucky not being helpful. Yes. So our final exam is on the 17th of December. The start time is 10:15. Okay, so it is 15 minutes earlier than the lecture time. So make sure that you adjust your alarm clock or whatever you use to remind you when to get to class. You have to turn it back 15 minutes. Okay. The exam is 2 hours long. Okay. So if I were you, I would plan to be on campus in this building by maybe about 10 o'clock. Okay, so you have some time to just kind of sit down, quiet down, get you hydrated and whatnot. And then, we'll start the exam at exactly 10:15. It's open book, open notes. You can bring a calculator, okay, but no electronic devices otherwise. I will be projecting the clock on the projector, just like exam one and exam two. So you kind of have to time yourself. I believe that should be enough time. Okay, if you know the material, that should be enough time to finish the whole thing. Um, so having some practice ahead of time definitely helps. Instead of trying to figure out in the exam, what is this construct doing, or what is this statement is trying to do. If you are familiar with those concepts already before the exam, it helps tremendously. So are we good so far with the final exam? When it is, what you can bring with you, basically the same restrictions as the regular exam one and exam two. All right. Yeah. How do other professors do this? Do they usually allow or not allow bathroom breaks? But what if somebody has a phone and they don't put it down? Do we use a scanner to kind of? Oh, okay. But somebody can still have two phones, right? They put one on the desk. Because I'm not gonna pat you guys down, okay? I'm not gonna give you a free massage. If you want a massage, pay me, okay? So I'm not gonna give you a free massage by patting you down, okay? So yes, yep. I, y- I don't like the idea of no bathroom break, but at the same time, because of the experience of another class, okay, it's no one from this classroom, but because of that experience, it's like, you know, so I'll I'll decide, okay. Do you guys, does anyone has a medical need to go to bathroom like frequently? No, okay. Okay. Yeah, well, me too. I tend to do that too. But 2 hours is not too long. Okay. If I go to bathroom right before the exam, I'm usually okay. So, yep. So I think for now we're gonna keep that policy. Okay. But I'll think about it. Okay. I'll keep thinking about it. All right. Anything else? We don't have a lab today. Okay. This is just a programming assignment. Okay. So if you want to do it here, or if you want me to take a look at Rhythm Spider, I can do that. If you are going like, okay, I got everything that I need, I can do the coding by myself in my cave, you know, you can go back to your cave and do your programming. That's fine. Okay, so we're gonna have a earlier dismissal today, and I'll see you guys next Monday. Have a nice Thanksgiving, and I'll see you over the weekend. All right, let me stop the mic first, and then I'll take a look.